thank you. So actually, it's a bit confusing. I'm currently a postdoc at the Center for Pediatric Oncology, but I did this work as part of my PhD at the University Medical Center Utrecht. Different hospital, same city, different group. So today I'll be presenting this method that we've developed. And we actually recently put the preprint online, and if you scan this QR code, you'll be brought to the preprint on bioRxiv. So let me first introduce what we mean when we're talking about shared SNPs or pleiotropic SNPs. So let's say that we're looking at the results of a GWAS on type 2 diabetes, T2D, and another GWAS on rheumatoid arthritis, RA. And we might expect some SNPs, like SNPs involved in insulin signaling, to be only associated to T2D and others only to RA. But some SNPs, specifically those that are involved in the immune system, would be expected to be associated with both traits. This is all hypothetical and it's just an example, but just to give you an idea. Because both these traits are immune related, we would indeed expect these SNPs that are involved in the immune system to be associated to both traits. And so if we can find these SNPs, then we could potentially learn more about SNPs for which we don't really know what their function is yet. We can also better understand the underlying processes of traits and which of those are specific to the trait and which are shared with others. And in this way, we can also find traits that actually share underlying processes while they are not overall correlated. And now, first, to give you an intuition of how we will identify these pleiotropic SNPs later on, I first want to look at this visualization where each point is a SNP. And the x-axis indicates the effect size of the SNP on T2D, and the y-axis indicates the effect size of each SNP on RA. And we see that some SNPs, like these, only have an effect on T2D, others only have an effect on RA, but some, the orange ones in this visualization, have an effect on both T2D and RA. And where I say has an effect on, I actually mean is associated with, of course. And so the processes from the previous example would show up in these places in the plot. Joint inflammation very specific to RA, the immune system here shared. But before we move on with the analysis, we first have to actually define what is pleiotropy and what kinds of pleiotropy can we observe. So the first type of pleiotropy is probably what we think of, is a SNP that has a direct effect on one trait and also a direct effect on another trait. This is called horizontal pleiotropy or direct unmediated pleiotropy, and this is the type of pleiotropy that we are actually interested in this case. There is another type of pleiotropy where one SNP has a direct effect on only one of the traits, but because this trait is correlated with another trait, we will also see an association of this SNP with T2D in this example, while the SNP only has a direct effect on RA. And if we would remove this correlation between those traits, we would not see an association with this SNP and T2D anymore. Because the pleiotropy here is mediated by the correlation between the traits. And because we were only interested in the direct pleiotropy, the horizontal, we perform a decorrelation transform, also called a whitening transform, where we use the covariance matrix to correct for the correlation between the traits, and then this is what we end up with, uncorrelated data. So we first do that, And then we will only find horizontally pleiotropic SNPs and not vertically pleiotropic SNPs. So now we can go back and actually think of a definition of a shared SNP. So the first thing we should observe is that for a SNP to have a shared effect on multiple traits, it needs to have an effect at all. So a large distance from the origin, because all these SNPs in the middle don't really have an effect on anything. Each SNP should also have a certain angle with the x-axis that's very close to a quarter pi or 45 degrees in this case. And this distance and this angle theta are actually polar coordinates, which can readily be calculated from the effect sizes. So directly from the GWAS summary statistics, we can calculate for each SNP a distance and an angle. And for the shared SNPs, this angle can actually also be in any of the other 4 quadrants. And because each quadrant is equally shared in our eyes, the only thing that changes is the direction of effect in the original GWAS. Because they are equally shared, we basically fold these quadrants on top of each other. So this is equal to taking the absolute value of the effect sizes. And then they're all on top of each other. And then we stretch the data, or we multiply the angle by 4. And this is just to make sure that the data still describes a whole circle. And that's important for the further analysis. So now we can go one step further and ask ourselves, okay, which distance is large enough? And for this, the goal of this step is to get rid of these SNPs in the middle that don't have an effect at all. And the null hypothesis for these SNPs is that they are from a central chi-distribution with 2 degrees of freedom, because the distance is actually a square root of a sum of squared normally distributed values. So that's the definition of a chi-distributed variable. And the 2 degrees of freedom in this case because we're looking at 2 traits. So we can use this to calculate p-values for the distances for each SNP. And this allows us to filter out these SNPs in the middle. So this is our first step. And then with the remaining steps, we actually look at the value of the angle that we calculated. So the fourfold transform of the angle, theta trans, it's close to pi for the shared SNPs after this fourfold transform. And the null hypothesis is then that this angle is equal to 0. And to test this, we use the von Mises distribution, which is equivalent to a normal distribution for circular data that takes into account that a circle doesn't really have a beginning or an end, and 0 and 2 pi are equal to each other. And this statistical distribution has an angular mean, which we've already said should be equal to 0 under the null hypothesis, and a concentration parameter kappa. And this was a bit more difficult to estimate. This is similar to the inverse of the variance in a normal distribution. But we were thinking about this, and we thought that it might actually depend on the distance, because this concentration parameter basically tells us how spread out the data is. And remember, the data that we're looking at is angles. So if the each SNP actually comes from a bivariate normal distribution, so here I've simulated the distribution of one SNP actually, and we see that as it moves further away from the origin, the spread in the angles gets smaller and smaller, while the spread in the original data is exactly the same. So I've simulated this, and then using existing functions in the circular package in R, I've calculated the value of kappa for this simulated data. And we see that indeed it depends on the value of R. So we use this to put in the exact value of kappa that is estimated from this function in the von Mises distribution. And now we can also calculate p-values for the angle of each SNP. That tells us how likely it is that that SNP does not have a shared effect, is trait specific. So now I quickly want to show you application of photomorphism to 2 traits, and then later on I will also go into an application on multiple traits. So we've applied our method to ischemic stroke, which is a brain infarction, and myocardial infarction, which is a heart infarction. So we already expected to be some overlap here. So we expected some shared SNPs. And here I'm comparing here in red SNPs that were significant for ischemic stroke in the original GWAS, SNPs that were significant for myocardial infarction in the original GWAS. And then if we only consider the lower 2 circles, their intersection tells us which SNPs were found to be significant for both traits only based on the original GWAS, so without using our method. But then here on top, we see the SNPs that are identified as being shared by PolarMorphism. And we see that PolarMorphism identifies all these 59 SNPs that we could already identify without using our method. But it identifies many more, some of which were only found to be associated with one of the traits, and some, these 41 here, were not identified by any of the original GWAS. And here I just wanted to show what the data looks like after we've applied our method. On the left is a similar type of plot that I showed in the beginning with example data, but now this time with real data. And we see the gray ones are not shared. So the ones in the middle are the ones that we lost with the filtering step on distance because they don't really have an effect. But these here do have a large distance, but they are very specific to ischemic stroke in this case. And then in orange, I've plotted all the SNPs that were found by PolarMorphism. And on the right, it's the same data, but now on the x-axis we see sharedness, which is basically this transformed angle. So the closer to 1, the more shared the SNP is. And on the y-axis, we see the distance r. So now we make a first step towards analysis of multiple traits. But this is actually still based on pairwise analysis, because up until now, I've always been talking about both traits, trait 1 and trait 2, and finding SNPs that are shared between the 2. That's what we did here, but we applied it to almost 50 traits and did all combinations. And afterwards, we created a network where each edge, so each connection, tells us how many SNPs are found to be shared by polymorphism for the 2 traits under consideration. And we can make a few observations from this graph. First, it's very densely connected. A lot of the edges or connections that could be drawn, that are possible, are actually found here, more than 50%. And we also see that some domains, I won't go too much into detail today about the domains, but I've colored them on domain. And we see that some of the domains are fully connected. So all the nodes in a domain are all connected to each other. For instance, in the lipid domain here in light blue, and here the blood pressure domain. And we also see that there are many SNPs shared between these. And then another thing we wanted to look at, and I see, by the way, that part of the figure here is missing, but it's not a big problem. One of the things we were thinking about is some of the information, especially on trait level, can also be gotten from genetic correlation. So genetic correlation is one value that tells us overall how genetically similar are two traits. Or how genetically similar are the genetic associations to each trait. And so we decided to test it, and we used the same traits as in the previous slide, and we calculated genetic correlation between each trait. And then we compared the two networks that we got. And here in blue, I show the subgraph for the subnetwork of all the trait combinations that share SNPs. So they were in the first polymorphism network, but they are not significantly genetically correlated. And this can happen if some SNPs are shared, but the rest of the genetic architecture of the traits is independent. Here in pink on top, we see trait pairs that are genetically correlated but do not share SNPs. And this can indicate, or this probably indicates, that these SNPs do share a lot of vertically pleiotropic SNPs, where we see associations for one SNP on both traits, but it's only because of the correlation between traits that they are associated to both, and they don't actually have an effect on both traits. And here on the bottom right are the traits that both share SNPs and are genetically correlated. So this is a combination of the previous two situations. And we see that by far most trait pairs at least share SNPs. And now, very quickly, I wanted to talk about applying polymorphism to more than two traits. But as you can imagine, so the idea, first of all, is actually similar to the situation for two dimensions, but it's more difficult to calculate. So we still get, in a multidimensional space, we can still calculate a distance from the origin. That's actually rather straightforward. It's a very straightforward extension of distance in two dimensions. The angle is much more difficult to calculate, but it's still one angle. And I try to visualize this, but as you can imagine, 3 dimensions is already difficult to visualize, and even more dimensions is just impossible to visualize. So here I show an example where we applied polymorphism to HDL, high density lipoprotein, LDL, low density lipoprotein, and TC, which is total cholesterol. So these are 3 of the lipid traits that I showed also in the network. They were very closely connected. And each point here is again a SNP with three coordinates for each of the 3 traits. So if we consider this SNP, for instance, we can draw a vector from the origin to it, which tells us the distance already. And this gray arc and line I've only drawn just to make it clear that this SNP is not along one of the axes, but it's, here. And now the null hypothesis, and this is a bit different from how I explained the situation in 2 dimensions, but it is actually equivalent, and you can look up the methods in our preprint if you want. So the null hypothesis is always along one of the axes, because the null hypothesis is that the effect is trait-specific and not shared. And now we want to know the angle between the SNP and the place where we expected it to be. So this angle. And again, I won't explain how we calculate it, but you can look up the details. So now, again, we have a distance r and an angle. which is actually not called data anymore, but terminology is not so important now. And now we can do almost the same as the situation for 2 dimensions. For the distance, we just change the degree of freedom, and the angle is actually exactly the same, because the angle is still describing a difference between 2 vectors in 2 dimensions. And we wanted to compare this, of course, to the pairwise analyses, because, yeah, it sounds nice that you can readily apply our method to multiple traits, but is it necessary? And to answer this question, we again looked at the lipid domain, at all 4 traits actually. And as you can see, if we want to do pairwise analyses for all these traits, we have to do 6 analyses, which we did. And then we took the intersect of each polymorphism analysis, because that gives us the SNPs that are shared with all trait combinations. And we compared this to the joint analysis. So this is what I explained in the slide before. And if we do this, we only have to do 1 analysis, and we find many more shared loci. So as you can see, I'm talking about loci here and not SNPs. We clumped the results to make sure that it's really independent genetic loci. And we also looked, we did a pathway analysis based on results from both these analyses. And this can be found in the preprint again. But just to make sure that we don't only find more loci, which is nice, but it's also more biologically relevant. Oh yeah, I already mentioned the preprint. We also published an R package, so you can apply our method yourself. And the details for the R package are also can be found in our preprint. So to conclude, we have developed PolarMorphism, which is a new method that can identify shared or pleiotropic SNPs. It works on summary statistics, which is really nice because they are usually publicly available. And because it uses parametric distributions, the chi distribution and the von Mises distribution, you don't need to, the user doesn't need to simulate any data. We did simulate some data to estimate this kappa parameter, but this means that it's relatively fast. And as I said, the R package is available on GitHub. And here again is the QR code to the preprint, if you want to scan it. And as I mentioned, I did this work as part of my PhD at the UMC, the University Medical Center in Utrecht. I was supervised by Jeroen de Ridder and Sander van der Laan, and helped immensely by a bachelor student, Michelle ten Dam, who really did a lot of work. And I also want to thank René Eijkemans for discussing some statistics with us. So thank you for listening.
Thank you, Joanna. That was a great talk. It looks like we've already got 1 question in the Q&A. Feel free to ask questions via the Q&A or the chat. The first question is, does the package require any specific kind of training, or can it be run out of the box?
Oh, that's a really nice question. So I've tried my best to at least document the functions. Well, first of all, it's an R package. So some basic knowledge of R or someone who can help you get started is required. But I've documented the function so that you can do like question mark and then the function name, and it will explain to you a little bit how you should use it. But I assume that I am a bit biased because I've been working in bioinformatics for years now and I really like programming. So I can say, yeah, it's super easy to use, but that might not be the case for everyone. Yeah, other than that, I also included, what's it called, an R notebook with examples that you can use as a starting point. But I would say people with at least basic programming and bioinformatics knowledge should be able to run it. And if not, please just send a question or something similar on the GitHub and I'll look into it.
Can you comment briefly on the runtime and the computational requirements?
Yes, runtime. I don't know the details by head, but this is also in the preprint, and we also compare it to some existing methods, actually. Computational requirements, it's also a good question. I would say it's mainly R and RStudio that's making it difficult. But that's something that I should probably specify. I hadn't thought of that. Should write it down. But it's not very heavy, basically.
Sure. So a scientific question. Have you explored the relation of pleiotropic SNPs with previously described comorbidities?
Oh, let me think about that question. The relation. So, if I understand the question correctly, previously described comorbidities, like for these lipids, for instance, we know that if you're, I'm forgetting the details, but I think if your HDL is high, your LDL is low, usually, something like that. I think that's what is meant here.
Possibly. Sometimes you get, for example, comorbidities between different diagnoses. People get diagnosed with one disease and they're more likely to get diagnosed with another.
Oh, of course. Yeah. So then in that case, not exactly like that. We did look into genetic correlation, like I said, but comorbidities is not the same as genetic correlation, or not always at least. So not exactly, no. But we do dive a bit more, and that's something I didn't present today. We dive a bit more into the stroke domain, just because my previous work was also in ischemic stroke, and we were able to say a bit more about that, biologically speaking. But we didn't do exactly what was suggested here, no.
Well, I guess maybe a couple more quick questions if there's time, and then we'll switch.
If possible, I would do a live question, if there is no.
Go ahead.
I have some curiosity about the data set that you used, or what would be more or less the size of the data, because I imagine you start from GWAS study, right? And then at some point, I think, depending on the sites, I believe that the statistics can be a little bit more or less powerful, depending also on the frequency of the variants that you are considering. So can you comment a little bit on this? And second question is, would be in principle possible to do similar analysis focusing on genomic regions? Because I think that somehow you could potentially, in case where, for example, you want to consider more rare variants, you can actually consider a genomic region and try to see all the different variants that occurs in that region as a unique variants, and identify relationship between traits and genomic regions instead of variants.
Yeah, let me answer the last question first, because I remember it more clearly. Definitely, it's possible to look at genomic ranges instead of SNPs. You just do need to think of a way to summarize the effect sizes that you find in a genomic range. But that is a good way to, I forget the name, lower the number of features. So that's in general a good idea, I think. But it is really important how you summarize the data. Do you just take the average effect size or something else? So that's not trivial. But other than that, it's definitely possible. The method doesn't expect SNPs. It just wants rows with an effect size, basically. And your first question, I forgot exactly what you asked, sorry.
The size of the data set you need, depending on the type of SNPs you are considering.
The size of the data set, well, most of it works on a SNP per SNP basis, but we do need to calculate the covariance between the traits because we use that to decorrelate the data. So the user either has to supply their own covariance matrix, and then the method can be run on only a few SNPs. But if not, we really need genome-wide data. so the full set of summary statistics.
Yeah, well, what is the size of GWAS data? So how many individuals more or less you?
Oh,
need?
individuals. Oh, I'm sorry. Well, that's something I would leave to the user, I think, because the general QC of that you do after a GWAS still has to be done. And it depends on so many things that I don't want to impose that. But QC has to be done by the user first, and then they can use our method on the summary statistics.